Hello and howdy, ladies and gentlemen. Root Beer here, of course. Looking at our 2016 Pascal paper, we are on the second last question, question number 24. 10 very small rubber balls begin equally spaced inside a 55-meter long tube. Okay. I'm assuming these answers here, they're just catching my eye. They represent the balls in the tube in some fashion. And it would appear that they sort of start away from the end and they're sort of equally spaced here. And 55 is a multiple of 11, so that should make sense. I guess the distance between these balls would be 5 meters. Anyway, they instantly begin to roll inside the tube at a constant velocity of 1 meter per second. When a ball reaches an end of the tube, so it falls out of the tube. So if these are the tubes, then these holes at the end are open. When two balls bump into each other, they both instantly reverse direction but continue to roll at 1 meter per second. 5 configurations giving the initial direction of the movements of the ball are shown. So that's what we've got. And so this ball right here, which I'm realizing was already black, let's make it red. So this ball right here is already heading for this opening here, whereas, say, this ball down here has already started heading towards this opening. And so, if I'm right, and they are 5 meters from the end, it would take them 5 seconds to drop out. Alright, so 5 configurations are shown. All gaps indicated in the diagram are the same length and are equal in length to the distance from the ends of the tube to the nearest ball. Yeah, that's what you said with equally spaced. Okay. For which configurations, I assume which of these 5 configurations, will it take the least time for more than half the balls, more than half, so 6 or more, of the balls to fall out of the tube? Okay. Now, the thing that I think is probably going to be key is simplifying this. And when two balls bump into each other, they just sort of instantly reverse directions, but continue rolling on. Okay? So what we've got here in physics terms is something that's called a completely elastic collision. No energy is lost, no velocity is lost. And there's a cute little trick I'll show you in a moment, but I just want to say that I would say the way to do this question, if you're not thinking through it, if you're not actually, if you're just trying to brute force an answer, the way to do that would be to start with each configuration. Here I'll show you just a smaller configuration, and then work out what happens in, say, 5-second intervals, just because that's how long it'll take for, actually no, 2.5-second intervals. Eventually these two balls here will meet together. And this one will be half on its way out, but they'll bump into each other and they'll completely reverse direction. And so what'll happen is, after a period of time, they'll be back to where they started. This guy will have since popped all the way out. And they will, so this would be 0 seconds, 2.5 seconds, and 5 seconds. So these two balls will be back to where they started, in a sense. I mean, but they're heading in opposite directions. And, that's fine. But with more balls, you're going to have, more collisions, and you're going to have to do a very, very long sequence of tube sort of diagrams and keep track of time. And that's okay. That's a way to do it. That's a way to brute force a solution. But what we've really got here is when they collide, we can, and this physics teacher taught me this a long time ago, because it's because the velocities don't really change. You can think of these two balls as bouncing off of each other, or you could imagine that they're not really hitting each other. Because what would happen if these were, say, I don't know, ghost balls? They could just sort of pass right through each other. And so you'd have the blue one here and the blue one here, and it would just pass on through. So other than knowing that the balls have actually switched, it's still the same sort of picture. And if you view it that way, as though the balls are just passing through each other, then it's a lot easier to keep track of the blue ball. He's not bouncing back and forth, he's just sort of slowly ghosting through everyone on its way out. And you get to keep sort of these same pictures over and over again, but it's a lot easier to compute with because, well, how long is it going to take the blue ball to get out? Well, how far away is it from the tube in the direction it's going? Now, of course, the blue ball, in reality, actually bounces off. Okay? But you could sort of pretend that when they collide, the colors swap. And this is an interesting way to sort of conserve our calculations or reduce the number of calculations. So you could instead imagine the balls are, I guess, ghost balls and pass through each other. Or you could imagine that the collisions are so violent the colors actually swap, but you get the same sort of picture in the end. The balls are still moving in their directions and everything else, but it makes it a lot easier to calculate how long it takes each ball to drop out of the tube if you can imagine the balls just sort of passing through. Now, this would not work if, for example, the collision between two balls halved their speeds or anything like that. The only way I know to do a question like that would be to actually track all the interactions and everything like that. But we don't need to do that exactly. So, as I already said, 55-meter tube, 10 balls spaced, and space on the ends means the space between balls and the ends of the tube is 55 meters over 11. Why 11? Imagine if you just had two balls evenly spaced in the tube. Okay? How much space is there? Well, you're going from the end to a ball, from the ball to a ball, and from a ball to the end. That's 3. That's 1 more than the number of balls you've got. Similarly, if we had another ball in here, you'd break up one of these spacings and you'd have 4 equal spacings. Well, we've got 10 balls, so that's 11 spaces. So each one's going to be 5 meters. We don't actually need to know that distance, but I think it'll help for the timing calculations we make. Okay, so I guess we just need to start looking at our answers A, B, and C. So let's look at A. So A, we've got 3 balls heading towards the end. 1, 2, 3, and then another one coming back this way. 2 colliding, 2 going away. And 2 going away from each other again at the end. Okay. So this ball here is it's almost at the end. It's actually it's got to go 50 meters. It's got 50 meters to go, so it'll take 50 seconds for this ball or this ghost ball to move through things, or for the particle wave that the ball represents to propagate all the way to the end of a tube. It'll take 50 seconds. This one's a little bit closer. Remember, the gaps here are 5 meters, so getting closer to an end means we decrease. So we'll get 45 seconds. This one will take 40 seconds for a ball to leave. This one here, this ball here is 1, 2, 3, 4. So 4 times 5, so 20 meters. So 20 seconds for that ball to leave. 30 seconds. 30 seconds for this one. 35. This one is 1, 2, 3. So 15. 40. No, this should be 45. And this one here at the end will take just 5 seconds to cross this gap and exit the tube. Okay, so that's tube A. And how long does it take for at least 6 balls to get out? So 5 seconds for 1 ball, 15 for 2 balls, 20 seconds for 3, 30 seconds for 5 balls to leave, 35 seconds for 6 balls. Okay. How about B, C? I might be able to fit D on here as well. We'll see. Let's do it like this. Away, forward, away. So that'll be 5, 5, and 50 again. The opposites. So 45, 10, 45. Close, close, away. So that'll be 40, 15, 15. Away, away, close. So that'll be 20, 35, 35. Away, away, away. So all of those should be 30 seconds. Away, close, close. So away, that'll be 25. Close, close. So that'll be 30 for each of those. Again, away, close, close. Or I guess I should be saying right, left, left. I don't know why I'm saying close. Closer to the left-hand side, I guess, technically. Left, right, left, and then 3 lefts. So that will be 40, and there's another 40, and that'll be 15, 45, 45, 45, and left, right, right. So that'll be a 50 seconds for that to leave, 5 and 5. Okay, so this first one, 5 seconds for 1, 15 for 2, 20 for 3, 25 for 4, 30 for 5, 35 for 6, and, 35 for 6 again. So, neither A nor B can be the answer. Remember, for your Pascal contest, there's always guaranteed one answer, so anything else that takes 35 seconds is automatically out as well. Unless they all do, in which case maybe I've mistaken the process by which we should do the answer. Anyway, 5, 10, 2, 15, so that's 4 balls after 15 seconds. And we have a new winner, so it takes 30 seconds for C for 6 balls to leave. 5, 5, 20, 30... So again, 35. So it looks like C is the answer. It could be E. I haven't done E yet, but it certainly looks like C is the answer. So if somebody called time right now, I would guess C. Left, right, left, right, left, right. Or right, left, actually. Are those far enough apart? I don't know. Then left, right, left, left. So that'll be 50, 45, 35, 30, So that means this one's also 30. That'll be 15, 50, 10, 40, 20. So 15 seconds for 2 balls to leave. 20, 2 30s, that's 5 balls after 30 seconds, 35 once again. And so our answer is C. Okay, so C, it takes 30 seconds for 6 balls to leave. Okay, that's kind of nice. I would say this is not necessarily an easy question. I've seen these, as I said, I've seen this sort of a question before in a physics scenario, where they were trying to show you how you can simplify a system when you've got completely elastic collisions. So physics does pay every once in a while, but it's an interesting question overall. I liked it. It certainly took a little while to write things down, so this could very easily be a time sink question. And when you realize that you're doing a question that's sort of eating up a lot of time, you might instead try, say, question 25. I don't know what question 25 is going to involve yet, but it's entirely possible that it won't have as many interactions, as many things to worry about and write down and play around with. So just because it's 25 does not necessarily mean it's harder than 24. I mean, 24 could be easier than 25, but 24 might just take more time. That's also a possibility. And remember, time management is key when you only have an hour to do the paper. There we go. Our answer is C. Up next will be question 25, and that will finish off our Pascal paper.